Hi, so we'll be talking about classical mechanics, and this will be a playlist in which we will focus on different topics in physics, but we'll focus on higher level concepts. So undergrad physics students can follow this playlist, and we are starting with classical mechanics, but eventually we'll move on to quantum mechanics and electrodynamics, thermodynamics. And one other thing is that we will not follow the standard course outline. Uh, we'll be we'll try to develop a conceptual understanding of what is the meaning of each of these concepts and how they are interconnected. In this first video, I just want to give you an overview of classical mechanics. Okay, so this will be like a bird's eye view of classical mechanics. Okay, let's start with our ultimate goal in classical mechanics. So the ultimate goal is to predict the future. Okay, we want to predict the future. Now, the problem with this kind of goal is that if you want to predict better future, you have to have a really good understanding of the present, right? If you don't know what your starting condition is, you cannot predict the future. So to achieve this goal, that is predicting the future of any system that we are studying, we need to understand the current state of the system, right? So then this word that we need to understand in classical mechanics is the concept of state of a system. So what do we mean by state of a system? State of a system is the minimum set of variables, or you can say minimum set of information that you need in order to predict the future. So each theory, each framework will ask you for certain starting inputs, and then the theory will turn its wheels and give you the output, right? Tell you what the future will look like after a certain time. So the framework, the initial conditions that you put into the framework define the state of your system. So this concept of state is very important because what follows will depend on how you define your present state of the system. Okay, now what are different options to represent the state of the system? And this motivates us to introduce another concept in classical mechanics, that is the concept of mathematical spaces. So mathematical spaces, what do I mean by mathematical spaces? So for example, if you are working in 3D physical space, so what we have is, for example, like these three axes, X, Y, and Z. And what we can do is we can define a unit vector in the direction of X, Y, and Z. So this unit vector I will point in the X direction, this unit vector J will point in Y, and this unit vector K will be pointing in the Z direction. The mathematical word is that these three basis vectors, span our 3D physical space. Okay. Now, I know these things, like right now, it sounds very maybe trivial or very basic, but you will see very soon it gets very complicated. Okay, and if you don't understand these basics, then you will be lost. You will understand individual concepts, but you will not know the connection between them. Okay, so we say that any mathematical space will have some basis vectors. And what are basis vectors? Basis vectors is the minimum number of vectors, minimum number of orthogonal vectors. Orthogonal means that if you move in one basis vector, your position in the other axis will not be affected, right? So if, for example, you are here and I move in X direction, my position in the Y and Z direction will not change. So in other words, they are orthogonal. So each mathematical space will be spanned by some orthogonal basis vectors, and basis vector is the minimum number of orthogonal vectors that span the space. What do I mean by spanning the space? Spanning the space means that any point in that space can be represented in terms of these basis vectors. So this vector, or any vector in 3D space, can be represented in terms of these basis vectors. Now, the question is, do we have some other options for mathematical spaces? And that's where things get interesting and also complicated. So the answer is yes, we can work in other mathematical spaces. An example of another mathematical space other than the physical space is what we call configuration space. So what do we mean by configuration space? So imagine that our system is composed of two particles, okay? So two particles that are only allowed to move in one dimension. So this is particle 1 or particle A, and this particle can only move in one dimension, and right now let's say this particle is at position 3, okay? And then I have another particle which again can only move in one dimension, and this time this second particle, let's call it B. Let's say this particle B is at position 2, okay? So something like this. Now my question is, can I represent the position of particle A and particle B with a single point? Or how can we tell the configuration of our system by a single point, right? That's where this word configuration space comes from. You want to specify the configuration of your system, which means specifying where is each particle located. You have to tell the position of each particle in your system. Right now in our system, we only have two particles. So we want to specify the position of these two particles with a single point in some configuration space. So what we can do is, if I rotate this axis along which the particle B can move, if I rotate it like this so that it becomes orthogonal to the space of particle A, which is again a one-dimensional space, and I superimpose these two spaces like this, now you see what I get is a two-dimensional space, right? This two-dimensional space will be called configuration space. And the reason we call it configuration space, because in this space, if I draw a single point like this point is giving me information about two particles. This point tells me that particle A is at position 3 and particle B is at position 2. Now you can imagine that if you have, for example, 3 particles, each of which is allowed only to move in one dimension, then what you can do is you can again draw another axis, third axis, make sure that it is orthogonal to these two and superimpose it on top of this. Then you will have a three-dimensional configuration space, and each point in that configuration space, a single point, will tell you the position of 3 particles which are only allowed to move in one dimension, right? Now I'm making the particles move in one dimension only because of course if I make A to move in 3 dimensions and B also to move in 3 dimensions and then make their spaces orthogonal to each other, I'll have a 6-dimensional orthogonal space, which is difficult to imagine, or even it's impossible actually to imagine, and you don't have to imagine. That's why we call them mathematical spaces, right? These are abstract spaces. So that's why we define this idea of basis vectors spanning some space, some mathematical space. And you will see when we go to quantum mechanics, these spaces will be completely abstract. Right now, you can somehow think of it as a physical space, 2-dimensional or something. But the reality is you don't have to, right? You can just understand what it means, what the idea is by understanding the physical space, and then make this whole concept completely abstract and make different spaces. Now, how will you predict the future in configuration space? You will say that our system, which right now is represented by this single point in configuration space, this will evolve in time and it will follow some path in configuration space. So let's say as the time passes, the system evolves from point A to point B, and it will follow some path, right, in the configuration space. We have to predict the path that this system follows. The theory that we will use to predict the path that the system will follow will be different from the theory that we use to predict the evolution of the system in physical space. In physical space, the theory that tells us the evolution of system in physical space is called Newtonian Mechanics. But the theory which tells us the path that the system will follow in configuration space is the path is defined by a theory which we call Lagrangian Mechanics. So now in most of the cases when they start Lagrangian mechanics, they start with what Lagrangian is. Lagrangian is the difference between potential energy and kinetic energy, or I think it's kinetic energy minus potential energy, something like this, right? But they don't really explain what is Lagrangian mechanics. Why do we need Lagrangian mechanics? What is happening, right? And then after 3 or 4 weeks, they'll start Hamiltonian mechanics without mentioning why is it that we are using Hamiltonian mechanics. So the reason is that we are using different mathematical spaces. When you use physical space, you use Newtonian mechanics. When you go to configuration space, you work with Lagrangian mechanics. And then, as you can, maybe some of you can guess, that if you go to phase space, so phase space again is another mathematical space. In phase space, the path of the system from one point to another, the system goes from one point in phase space to another point in phase space, and the path that it follows from one point to another in time is defined by Hamiltonian mechanics. So Hamilton's equations will tell you how your system will evolve in time in phase space. So what is phase space now? You see here, when we were specifying the initial condition of particle A and particle B, we only mentioned its position, right? So where the particle is located. But if you were to specify both the position and the velocity or momentum of the particle, then you will be working in phase space. Now let's see what happens if we need another piece of information. So now I have a particle again, which is again just can move in one dimension. So it's one-dimensional particle, and let's say its position is this, and now I need another axis for its velocity. So this is position, and then I need another axis for the same particle, not another particle, for the same particle A. I need another axis that will specify its velocity, right? So let's say it has some velocity which has this value. Now, again, if I need to specify the position and the velocity of just one particle by a single point, I will do the same trick. I will rotate this axis, superimpose it with the position axis, and now a single point in this space, this is a phase space for a one-dimensional particle, and a single point in this phase space will give me information about the position and the momentum of a single particle. Now, you should be able to tell the difference between configuration space and phase space. Here, we could represent two one-dimensional particles in two-dimensional configuration space. So the way I've drawn it, the maximum dimensionality of this configuration space right now, it's 2D, because each particle can move only in one direction, and we have total 2 particles. So the total number of dimensions will be 2D. And here in phase space, each particle can move in only one direction, and we have only one particle, and still we get a 2D phase space, two-dimensional phase space. So you can see that phase space is a higher dimensional space. The dimensionality of phase space is higher than configuration space, and the reason is because we have to keep track of two separate things. We have to keep track of velocity, momentum, and we have to keep track of the position. Sorry, this shouldn't be velocity, it should be momentum. And because of this, even for a single particle, we get a two-dimensional phase space. Here, we were getting a two-dimensional configuration space for 2 particles. Now here, you can try this question. If I have 2 particles, so number of particles is 2, and both particles are allowed to move only in one dimension, what will be the dimension of phase space that we will be working in? The dimension will be 4D, right? Because we have 2 particles, each particle can only move in one dimension, but we need 2 axes for each particle, one for position and one for momentum. So the total number of dimensions will be 4. And you should remember that all of these dimensions will be orthogonal to each other, okay? That's an important point. And each of these dimensions will have a unit vector or a basis vector in that direction. So I hope these ideas are clear. And if you are doing physics in phase space, you are actually working in you're working with Hamiltonian mechanics. So Hamiltonian mechanics, or and the main object that you will be dealing with will be Hamiltonian of your system. So if you define the Hamiltonian of your system, then you can talk about how the Hamiltonian will evolve over time, or how the Hamiltonian will affect your system. Now, to quickly summarize all of these concepts, I just want to draw a diagram. So we have classical mechanics, and if you do classical mechanics in physical space, you get Newtonian mechanics. And in Newtonian mechanics, if you use Newton's laws, you get your equations of motion, right? Okay, second option is to work in configuration space. And if you do classical mechanics in configuration space, the field that you will be working in will be Lagrangian mechanics, And then, of course, you will not use Newton's laws. You will use Euler-Lagrange equations. So Euler-Lagrange equations to derive equations of motion. And third one, if you do classical mechanics in phase space, remember phase space uses both position and momentum of each particle. Depending, each particle can move in different dimensions. If it is moving in 3 dimensions and you have a single particle, phase space will be 6-dimensional for a single particle, because 3 dimensions for position and 3 dimensions for momentum. So even for a single particle, phase space will be 6-dimensional. And if you have more number of particles, phase space will increase by the same number. Okay, phase space, you'll be doing Hamiltonian mechanics, and then the framework or the formulation of theory that you will work with, the equations, will be called Hamilton's equations. And using Hamilton's equations, you will derive equations of motion for your system again. So that's kind of like the overview of classical mechanics. So if you understand this from like this bigger perspective, how these things are connected, then you can really understand what you are doing. Over the next few lectures, we'll be starting with configuration space, and then we'll move to phase space, and we will also derive Euler-Lagrange equation and Hamilton's equations. So I hope this was a good introduction of classical mechanics and how different things are connected. We'll be talking more about these mathematical spaces. For example, another famous mathematical space is what we call Hilbert space. Quantum mechanics is done in Hilbert space. So all the mathematical objects that we use in quantum mechanics, they are vectors in Hilbert space. We'll talk about the concept of vector, but right now you should understand that you don't really need to associate every single mathematical object with something physical. Okay, I think you should leave your imagination here, and that's it. After this point, everything that comes next will be abstract. All you need to understand that each mathematical space will have some basis vectors which will all be orthogonal to each other, and these basis vectors will span that space. So yes, I think that's it for this introduction, and see you in the next lesson.